Hi everybody, hope that you're doing well at home. Welcome back to AP Chemistry. We're going to pick up where we left off talking about chemical equilibrium. So chemical equilibrium is a dynamic equilibrium that happens when opposing reactions happen at the same rate. So what that means is that we've got the forward reaction and the reverse reaction happening at the same rate. At equilibrium, the concentrations of everything stop changing, and so it looks like the reaction has stopped. So when we say a reaction has reached equilibrium, it's not that nothing is happening, but that the concentrations have stopped changing. So it looks like the reaction has stopped. So if we take a typical chemical reaction here, so we've got A and B as our reactants, D and E as our products, we can set up what's called an equilibrium expression. So the equilibrium expression has this value Kc. This is our equilibrium constant, and we set it equal to the concentration of our products raised to the power of their coefficients divided by the concentrations of the reactants raised to the power of their coefficients. Now this equilibrium expression is in terms of concentration, but remember that we can also set up an equilibrium expression in terms of pressure if we have gases. Also remember that only reactants and products that are either aqueous or gases can be included in the equilibrium expression. If you have a solid or a liquid, you just leave it out. You just totally do not include it in your equilibrium expression. All right, so thinking about the size of the equilibrium constant. So if we're looking at our equilibrium expression here, we can see again that it's products over reactants. And we want to think about what does it mean if the value for our equilibrium constant K is very big or very small. Right, so in this first situation, if K is much larger than 1, right, looking at our equilibrium expression, that's going to mean that our numerator is much larger than our denominator, which means that there's more reactants than products. Sorry, more products than reactants. All right, so large K, lots of product, not a lot of reactant. All right, and so we would say that equilibrium lies to the right, because on the right side of our equation is where we find the products. On the other hand, if K is really, really small, if it's much less than 1, then looking at our equilibrium expression, that means that the numerator is very small and the denominator is very large. So there's not a lot of products, and there is a lot of the reactants still in the reaction mixture. So we would say equilibrium lies to the left, so towards the reactants, because the reactants are on the left side of the equation, and there's much more reactants than products in our mixture. All right, so taking a look at these 3 examples, I want you to take a minute, look at what's going on in these images, and see if you can figure out which one is going to have the largest value for K and which one's going to have the smallest value for K. All right, so hopefully you have figured out that the more product is present, the larger your value of K. So if we take a look at these 3 examples here, we can see that the one in the middle has mostly reactant left over, mostly green, and only one little bit of product, one yellow here, right? So that would mean that there's much more reactant than product. That means that K is going to be very small, and it's going to be the smallest for number 2. For number 1 over here, we can see that red is our reactant, blue is our product, and we can see that we are forming more of the product here, but that we still have a good bit of reactant left over. So this should be our second largest value for K. And then if we look at number 3, where blue's our reactant and red's our product, we can see that we've formed almost entirely product with only a little bit of reactant left over. So number 3 is going to have the largest value for K, for the equilibrium constant. All right, now I want to talk about the equilibrium constant and what happens if we manipulate our chemical equation. What happens if we change the direction of the chemical equation, and what happens to K when we do that? All right, so taking a look at a reaction that we've looked at in the past, so N2O4 forming 2 NO2s. So at equilibrium, we can see that what's going on if we set up our equilibrium expression. So at equilibrium, if we plug in our equilibrium concentration of NO2 raised to the 2nd power divided by our equilibrium concentration of N2O4, we're going to get a value of 0.212 for our equilibrium constant, and that's going to be at 100 degrees Celsius. So remember, depending on the temperature, that will change our equilibrium constant. Now, notice that our equilibrium constant here is just a number with no unit. So this is the great thing about equilibrium constants, is that they do not have a unit. You don't have to worry about you don't have to worry about that at all. It's just going to be the number. Now, if we write the reaction in reverse, so if we take two NO2s and we turn that into N2O4, so we write our reverse reaction, then at equilibrium, our equilibrium expression is going to be the reciprocal here. So N2O4 divided by NO2 raised to the second power, right? And if we swap our values for the concentration there, then we have to take 1 over our equilibrium constant. So instead of 0.212, it's going to be 1 over 0.212, which gives us 4.72 here. So we can see that the reverse reaction goes more towards the products, while the forward reaction stays more as the reactant, which is the same thing. So either way, we're going to see that at equilibrium, we have more N2O4 than NO2. All right, so like I said, the equilibrium constant for reaction written in one direction is just the reciprocal of the equilibrium constant for the reaction written in the reverse direction. Now, we can also talk about ways that we can change the stoichiometry of the chemical equation and what that does to K. All right, so if we take the equilibrium constant of a reaction that has been multiplied by a number, that's going to be equal to the original equilibrium constant raised to that power. So what I mean by that, so if we take A plus B going to C plus D, and that's got some equilibrium constant K1, and then if we took that whole reaction and we multiplied it by some number N, so that, like times 2 or times 3 or whatever, then our equilibrium constant for that reaction would just be our original equilibrium constant raised to the power of whatever we multiplied our reaction by. In addition, if we have an equilibrium constant for a net reaction made up of 2 or more smaller reactions, then what we can do is take the product of the K's for the individual reactions, and that's going to give us K for our overall reaction. All right, so taking a look at this, if we've got A plus B going to C plus D, and that has some equilibrium constant K1, and then we've got a second reaction, C plus F goes to G plus A, and that also has an equilibrium constant K2, then our overall reaction, we're going to cancel out A because it's on both sides and C because it's on both sides, leaving us with B plus F going to D plus G. And so our equilibrium constant for that reaction, K3, is going to be equal to K1 times K2. All right, now, really importantly, we are not always at equilibrium, and it's important to be able to figure out, based on a certain set of conditions, what's going to happen to the reaction to get to equilibrium. Right? If we're not already there, how do we get there? All right, and so taking a look at this, if we have nitrogen gas plus hydrogen gas going to ammonia to NH3, we can see that the equilibrium constant for that reaction is 0.105 at 472 degrees Celsius. So remember that that small value of K means that at equilibrium, we've got more reactant than product. And in fact, this is a pretty small number, so we've kind of got significantly more of the reactant than the product. So if we mix these two gases together, not much is going to happen. All right, so in this example, let's say we've got 2 moles of hydrogen and 1 mole of nitrogen and 2 moles of ammonia, and we put those into a 1 liter container, right? So we want to think about what's going to happen in order for this reaction to get to equilibrium. All right. Now, what we're going to need to figure this out is something called the reaction quotient, which is Q, capital Q. And that's a number that we get by substituting in the reactant and product concentrations or pressures at any point during a reaction into our equilibrium constant expression. All right, so the expression is going to look just like K, but instead of plugging in the equilibrium values for concentration, we're going to plug in our current values. So in this case, you can see that if we plug in our equilibrium expression, and instead of saying K, we say Q, then we're going to get ammonia's concentration squared divided by the nitrogen concentration times the hydrogen concentration to the 3rd power. Now, in the question, you'll see that we're given moles and a volume, and so we need to convert that into molarity. So we want to take moles per liter. So 2 moles divided by 1 liter is still 2 molar, and so on. And so we plug in our values for concentration into our expression, and we can see that Q has a value of 0.5. All right, Now, if we want to compare that Q value of 0.5 to our K value of 0.105. So we can see here that Q is greater than K. All right. Now, thinking about what that means, if you plug in values to your reaction quotient expression and Q is exactly equal to K, then your reaction is already at equilibrium. If Q is greater than K, so if you plug in your values and Q is a bigger number than K, then that means that there's too much of the products and that the reaction is going to proceed from right to left. So it's going to go from product to make more reactant to get to equilibrium. If Q is less than K, that tells us that there are not enough products and too much of the reactants. So the reaction is going to go from left to right. So the reactants are going to form more product until they get to equilibrium. So thinking about our example that we just did, we saw that Q was greater than K. Q was 0.5 and K was 0.1 something. So what that means is at the conditions given, there was too much of the products and the equilibrium is going to shift towards the left to make more of the reactant. All right, so I want you to try one on your own here. So at 448 degrees Celsius, the equilibrium constant for the reaction below is 50.5. So this reaction is hydrogen gas plus iodine gas forming hydrogen iodide. Now what I want you to do is take a second and see if you can figure out which direction the reaction is going to go in to reach equilibrium. If you're starting with these amounts of HI, hydrogen gas, and iodine gas, this time in a 2-liter container. So take a second and figure that out, and then in just a second I'll show you the answer. All right, so if we take a look at this problem, I've got my balanced reaction right here, so hydrogen gas plus iodine forming 2HI, and you'll recall that the equilibrium constant is 50.5. All right, so if we set up our reaction quotient expression, Q is going to be equal to the concentration of HI squared divided by the concentration of hydrogen times the concentration of iodine. Now we have to remember that to get our concentrations, we want to take our number of moles and divide it by the number of liters. So I've divided everything by 2 because we had 2 liters. So our concentrations here are going to be 0.01 to the second power, 0.005 times 0.015. Now when we plug that into this expression, we can see that we get an answer of 1.33. Now in this case, Q is obviously much less than K. 1.33 is less than 50.5. So what that tells us is that there is not enough of the product present in our reaction, and so the reaction is going to keep proceeding to the right. So the reaction is going to shift to the right to form more product in this case before it gets to equilibrium. Okay, so that's where we're going to leave it for today. I'm going to post some questions on AP Classroom so that you can practice figuring out the direction of the reaction to reach equilibrium. I will see everybody on Thursday. Hope you have a good rest of your day.